Think about your last physics paper. If you're treating the difference between a crystal and an amorphous solid as just, some basic memorization task, you are taking a massive risk with your grade boundaries, literally leaving marks on the table. Today, we're cutting straight through the noise. We're going to use an exact courtroom-style formula to secure top-band marks by connecting instant, microscopic atomic arrangements to long-term macroscopic behavior.
Consider this statement. A crystal has a regular shape, while an amorphous solid is random. Now, I want you to step into the shoes of a Cambridge examiner for a second. Put this piece of evidence on trial. It sounds vaguely right, doesn't it? But here's the harsh truth. This gets 0 marks. Absolutely 0. Why? Because ordinary revision focuses on these really basic, everyday labels instead of the actual physical mechanisms. You're describing what an object looks like from the outside, but you're completely missing the microscopic foundation that solid-state physics actually demands. Stating the term without explaining the internal physics, that's exactly how top grades slip away.
And that right there is the ultimate exam trap. It's painful to see. Students constantly lose marks because they state the correct macroscopic term, but they totally failed to explain what's physically happening down at the atomic or carrier level. Or, and honestly, this is even worse, they throw out a real-world application without ever linking it back to the underlying macroscopic reason. This is exactly why ordinary revision completely fails. You can't just read a textbook definition and hope for the best. You have to work backward, from the physical phenomenon right down to the macroscopic picture. Otherwise, you've just got this scattered collection of facts. It might feel like learning, but when a question hits you with command words like explain or evaluate, that scattered knowledge jeopardizes your whole grade. We need a much more disciplined approach.
So here is the ultimate examiner cheat code. It's a 4-step framework, and it's an absolute game changer for securing those top band marks. Step 1, definition. Step 2, mechanism. Step 3, consequence. And Step 4, application. If you can confidently walk through these 4 stages in order, you are proving you understand the topic deeply enough to crush both short and extended exam questions. It perfectly tracks the transition from the raw concept to scientific reasoning to hard evidence, and finally to precise examiner wording. We're taking a journey from the invisible internal physics right out into the observable real world.
Let's break this down, starting with Step 1, the technical definition. We have to establish the exact boundaries between these two states so you never confuse related concepts. A crystal is a solid with a highly ordered, repeating atomic structure. An amorphous solid, on the flip side, is a solid that lacks that long-range atomic order. Notice what we're doing here. We aren't talking about the external geometric shape of a rock setting on a desk. Actually, scratch that. External shape doesn't matter at all here. We are talking strictly about internal atomic packing. Tightening up our language to use this exact technical vocabulary, that is our very first quick win.
Moving right along to Step 2, the mechanism. Let's look at this precise cause and effect timeline, because the scale here is just mind-blowing. Think of it like a Formula One pit stop, where every fraction of a second completely alters the outcome of the race. In one single nanosecond, the atomic packing locks into place. Because crystals possess that highly ordered packing, in the next millisecond, that exact order dictates the material's defect tolerance and its bonding direction. Fast forward to 1 second, and that atomic structure is now determining the solid's observable macroscopic behavior, how it reacts to applied force, energy, or electrical transport. And over a year, that initial nanosecond dictates the entire lifespan and durability of a real-world technological device. Instant microscopic arrangements completely control long-term structural behavior. It is all driven from the inside out.
Okay, time for Step 3, the consequence. I've got a pause and predict challenge for you right now. We know the atomic structure is highly ordered in a crystal, and it lacks that long-range order in an amorphous solid. Now try to connect that microscopic reality to a macroscopic, measurable physical effect. What actually happens to the energy transport? How does the material respond to an applied magnetic or electric field? How does ordered packing radically change the physical strength when you compare it to a random, amorphous structure? If you can confidently connect the internal physics to an observable consequence, you're thinking exactly like a top-tier candidate.
In just a moment, I'm going to show you the exact examiner clue that changes your answer completely. But first, you really need the framework that makes that clue incredibly obvious. You see, the clue isn't about just blindly memorizing more facts, it's about proving the connection. The examiner is actively hunting for one specific word. They want to see the word because, linking the micro to the macro. They need to see you interpreting the behavior of a solid strictly based on what happens internally.
If your answer doesn't build a strong, clear bridge between those invisible atoms and the visible consequence, well, you haven't given the examiner the clue they need to award you full marks.
Which brings us to the final piece, step 4, the application. This is where the physics gets real. Real materials used in electronics, aerospace, energy systems, they all behave differently precisely because that crystal arrangement controls the packing and bonding direction. We're talking about semiconductor wafers powering the device you're using right now. We're talking about the extreme defect tolerance demanded by aerospace turbine blades, structural alloys in massive engineering projects, even the brilliant optical properties of gemstones. It makes the physics totally concrete and memorable. A turbine blade surviving extreme heat and stress isn't magic. It is the direct, measurable result of crystalline atomic structure and bonding direction.
Now let's put all this theory into practice. We are going to operate on a broken paragraph in real time. I want you to spot the error, be the examiner, get your mental red pen ready, keep our 4-step framework in mind: definition, mechanism, consequence, application. When you see how a student might try to explain one of our real-world examples, like the turbine blade, you need to diagnose exactly where their cause and effect chain completely snaps. Then you have to perform the surgical fix to rescue that grade. Let's look at it.
Compare this scattered, weak statement on the left with the highly disciplined, cause and effect top band answer on the right. The flawed answer says, turbine blades use crystals because they are strong. Sure, it gives an application, but it completely fails to link it back to the underlying microscopic reason. It's a classic ordinary revision trap. Now look at the top band repair. Crystals possess ordered packing that controls defect tolerance, giving turbine blades durability. Do you see the massive difference there? It states the microscopic definition, ordered packing. It gives the mechanism and consequence, controls defect tolerance. And finally, it links it to the application, giving turbine blades durability. That is what a disciplined, high-scoring, top-band paragraph looks like.
To really lock this in for your exam, we are going to build a mental memory palace using 4 specific trigger questions. Number 1, what is it? That's your pure technical definition. Number 2, what changes inside? That is your internal microscopic mechanism. Number 3, what is observed outside? That's your measurable macroscopic consequence. And number 4, where does it matter? That is your real-world technology application. If you can sit down, close your textbook, and answer these 4 prompts out loud from memory, your knowledge of crystal versus amorphous solids is rock solid. You've officially connected cause and effect.
So, you now have the exact framework to perfectly explain solid structures. But here's the next big question. How do you spot the common traps waiting for you when you have to actually evaluate practical data linked to these concepts? Because knowing the theory is only half the battle. Cambridge exams are absolutely going to test your ability to evaluate raw data under intense time pressure. Think about how this applies to your next lab evaluation. You'll want to jump straight into our next explainer to uncover those hidden data traps before they catch you off guard. See you over there.